Well, that didn't work. Oh, it did work? Alright, so I guess this is working. Hello everyone, I'll get set up in just 1 second here. There we go. Alright. So today we want to learn some Haskell. Disclaimer, I already read some of this before. So like a lot of this will be review, but it's been a long time for me, and you know, it's hard to remember everything, so we'll try to like just make sure we know everything. Oh, I should have gotten water. Ah, well, all right, I'm gonna make a video out of this also, so I'll start that in just 1 second. All right, so do I have all the right things here? Yes, I think so. Here we go. Hello everyone, so we're going to be doing Haskell today. I know if you see my other videos, they're all over the place. We're doing COBOL, we're doing Nix, we're doing 650 assembly language, but you know, you can't help it when you have an interest and you want to do something. It's just like, just do it. So today I want to review the Haskell that I've already learned. And just like my other Learn With Me videos, basically it's like I'm going to be reading some book or resource. It's Learn You a Haskell for Great Good. It's open source, so you can follow along with me. And if you have any questions, then like you can just ask me in chat when I'm doing these streams, or like join the Discord server that'll be in the description eventually. And we'll just get right at it. So, all right. So the URL, it's called Learn You a Haskell for Great Good, but make sure you go to the GitHub. Oh, let's see. It's like Learn You a Haskell for Great Good, and then we do GitHub, because there's two versions. There's like the book you can get. Wait, is this the version? Learn You a Haskell, a community version. Yeah, this one's really cool. It's the one that like they took the original book that's famous and made a book, like updated it so that you can read it online. So how do you view this? I was just clicking on this one here, and it starts. This is an open source fork of original Learn You a Haskell. Read it online for free. Then I click on that, and now I'm here, and I think this is the right place because we're still on GitHub. So that's how you get there. I don't think we're gonna do too much today. We're just gonna like go slowly on this stuff. So this will be like a series where it'll take like several videos to get through all of it. So this one I won't read like word for word, because generally, like, you know, when I'm interested in a language, I'm already interested. You don't have to tell me what like all the details about it. I'll learn it as I learn the language, right? But yeah, it's important that you know that it's purely functional programming language. A lot of other, like Elixir is my main programming language, and the it's a functional programming language, but you can still do things like have side effects, like you can save things to the screen, to disk, or whatever. And but Haskell has this monad system that makes it very clear when that's happening. It's lazy evaluation, so we'll learn more about that. Statically typed. This is what I like about it the most, really, because like, oh my god, I'm not even sharing my screen. That is a big failure. Let's do that over again. Sorry for that one person who's watching. I didn't realize. So we're going to be learning Haskell today. There is a GitHub link that I'll be adding for Learn You a Haskell for Great Good. and it is a community open source book that is based on a very popular book teaching Haskell, but it's been updated by this open source effort. So we'll be using that. I'm going to be skipping a lot of this introduction reading because, I'm already interested in the language. It's purely functional. That part is it just means that there's no side effects that happen without you knowing it. Like if you're printing something on the screen or saving something to disk or the network, it clearly you have to know you're doing it. It's lazy evaluation. We'll learn more about that. It's statically typed, and this is what I like about Haskell the most because I use Elixir as my main language, but it's more dynamically typed. It's somewhere between dynamic and more than that. But Haskell is very has a strong typing system, and I just think that helps so much. Like when I programmed in Rust, it's like it caught so many errors that I didn't realize I was making. So that's really cool. Yeah, it's elegant and concise and all that kind of stuff. And best way to get started is download GH Cup. Well, I just want to get GHCI. So what I did here was I created a Nix shell, and I added GHC to it. I think I did a search here under the Nix packaging thing. If you don't use Nix, don't worry about it. But I made a whole bunch of videos on Nix, so I want to use it. So this will only take a second. So I found this, I added it, and then I ran my Nix shell here, and it got the stuff, and hopefully it will work. And I'll do the same over here. Right now I don't have GHCI, and then hopefully after running Nix shell here I will have it. Alright, so that is the main thing from this chapter. Starting out, ready to go. Let's get started. Look, there's a little egg. So we're the little we're cracking our eggs. If you're the sort of horrible person who doesn't read introductions to things and you skipped it, well, I am a horrible person. You might want to read the last section in the introduction anyway because it explains what you need to follow this tutorial and how we're going to load functions. The first thing we're going to do is run GHC's interactive mode call some function to get a very basic feel for Haskell. Open your terminal and type GHCI and you'll be greeted with something like this. All right, I'll use the bigger part for this here. Yeah. So that worked. 965. Looks like we're a little bit newer than what is here. Congratulations, you're in GHCI. Here's some simple arithmetic. Right, so 2 plus 15. 49 times 1000. That all seems to work. Now, what happens when I... yeah, 5 divided by 2 will give me a floating point number. So it doesn't do anything special to keep you in integer math. And that's something we noticed before when we were doing Nix. All right. So that's all self-explanatory, and it also supports parentheses. Well, I'm not going to bother typing that in. Pretty cool, huh? Yeah, I know it's not, but bear with me. A little pitfall to watch out for here is negating numbers. If we want to have a negative number, it's always best to surround it with parentheses. Doing 5 times -3 will make GHCI yell at you, but doing... Okay, let's see if it yells at us. 5 times -3. It did yell at us. Precedence parsing error cannot mix star, asterisk, and prefix minus in the same infix expression. I guess because it thinks that we're trying to use this as an operator. So we have to wrap it. We have to wrap this thing in parentheses. All right, cool. Feel free to type in chat if you have any questions or want to say anything. Um, that'd be fine. Boolean algebra is also pretty straightforward. As you probably know, ampersand ampersand means Boolean and pipe pipe vertical bar, like two of them, means Boolean, or not negates a true or a false. So we have true, yep, we have false, right. And I guess like true lowercase won't work, right. Okay, and then we know we have some of these operators. True, true and false is false. True and true is true, right? So we know all of that's going to work, and the not obviously negates. That all seems obvious. Testing for equality is done like so. It is with the equal sign. So 5 is equal to 5. I assume 1 won't work. Oh, I don't know what I ended up just doing there, but that can't be good. And then let's see, 1 equals 0. That's false. And then we need to use slash equal 5 to say 5 is not equal to 5, and that's false. But we can say 5 is not equal to 6, and that should be true. Okay, and we have string comparisons. And if we just change it, it's false. And now if I change this to a not equals, like this, then it is true. All right, perfect. What about doing 5 plus llama? All right, let's see. 5 plus llama. So we're adding 5 to a string, the number 5 to a string, and it doesn't like that. No instance for num string arising from the literal 5, the first argument of plus, namely 5 in the expression. All right, so it's definitely not happy about that. And when I compare two different types, like is 5 equal to true, it's also not happy. All right, so 5 is equal to hello, it's also not happy. Yikes, what GHCI is telling us here is that llama is not a number, and so it doesn't know how to add it to 5. Even if it wasn't llama, but 4, like 4 in quotes, or the number 4 in quotes, which all make it strings, Haskell still wouldn't consider it a number. The plus operator expects its left and right side to be numbers. If we tried to do true is equal 5, GHCI would tell us that the types don't match. Whereas plus works only on things that are considered numbers. Equal works on any two things that can be compared. But the catch is that they both have to be the same type of thing. You can't compare apples and oranges. We'll take a closer look at types a bit later. Note you can do 5 plus 4.0 because 5 is sneaky and can act like an integer or a floating point number. 4.0 can't act like an integer, so 5 is the one that has to adapt. All right, so that means we can do 4 plus 5.5, and that will work. Makes sense? Where are we? You may not have known it, but we've been using functions now all along. For instance, the asterisk operator is a function that takes two numbers and multiplies them. As you've seen, we call it by sandwiching it between them. This is what we call an infix function. Most functions that aren't used with numbers are prefix functions. Let's take a look at them. Functions are usually prefixed, so from now on we won't explicitly state that a function is of the prefix form. We'll just assume it. In most imperative languages, functions are called by writing the function name and then writing its parameters in parentheses, usually separated by commas. In Haskell, functions are called by writing the function name, a space, and then the parameters separated by spaces. For a start, we'll try calling one of the most boring functions in Haskell. I love these drawings. So this one is like, we're just starting, we're like a little chick. This one, like just trying to figure out, It's a little dated, but you tell me if I'm wrong. I'm guessing that what this is like, phone numbers have prefix numbers. So like I think that's like the first few digits of most phone numbers, and that's what they're trying to say here. Functions are usually prefix. Or is it that we're calling a function? So this is like calling a function. I don't know. It's kind of funny, like, to try to imagine. All right, so here's a boring function. Suck 8. 9. I guess it's like part of successor. Yeah, define successor. So maybe we shouldn't say suck 8. And returns the successor. As you can see, we separated the function name from the parameter with a space. Calling a function with several parameters is also simple. The function min and max take two things that can be put in an order, like integers. Min returns min returns the one that's lesser, and max returns the one that's greater. See for yourself. All right, so min 5 and 10, it gives us 5. Max 5 and 10 will give us 10, and I guess we can change the order and it'll still give us the right thing. Let's see if it works with negative numbers and floating point together. Okay, it didn't like that. All right, so it didn't like even negative numbers. It just did with positive integers. Is that what it said? Like integers. Well, that seems like it's false here, no? Oh, is this because of this? Yes, good thing we remembered. So it works with integers, and if I made this a floating point, it still works. All right, cool. So we just have to really remember that negative numbers can be confusing to write. Function application. Calling a function by putting a space after it and then typing out the parameters has the highest precedence of them all. What that means for us is that these two statements are equivalent. Successor 9 plus max 5, 4 plus 1. Successor 9, this takes one parameter, plus takes two parameters. Max 5 takes two parameters, plus 1. And I'm guessing they're talking about like these functions that are prefix functions. So if you put a space after it and then you type all the parameters, those are prefix ones, have the highest precedence. So this guy's going to grab his or her their parameters eagerly, and then the rest of it happens. That's what I'm guessing that means. However, if we want to call successor of the product of numbers 9 and 10, we would write successor 9 times 10, because that would get the successor of 9. We couldn't write. Yeah, that makes sense. So they are talking about prefix instead of these operators. So we have to write down successor 9 times 10. So this is what this should do, is basically give us 10 times 10, right? And that'll be 100. So if we want the successor of 990, we have to put that in parentheses. All right. We got it. If a function takes two parameters, we can also call it as an infix function by surrounding it with backticks. For instance, the div function takes two integer and does integral division between them. So this is like when I did the slash for division, that does not do integer division, but div does. So like div 5, 4 is just going to be 1, right? That makes sense. We'll do a bigger number so that we get something back. 90. 92 and 10 gives us 9. Makes sense. But when we call it like that, there may be some confusion as to which number is doing the division and which one is being divided. No, not really, but I can understand. So we can call it as an infix function by doing 92 div 10, and suddenly it's much clearer, only if it said divided by, but that's fine. Div 10. And it does the same thing. All right. A lot of people who come from imperative languages tend to stick to the notion that parentheses should denote function application. Oh, it's already like dunking on the C programmers. For example, in C, use parentheses to call functions like foo, bar1, baz3, comma, haha. Like we said, spaces are used for function application in Haskell, so those functions in Haskell would be foo, bar space 1, and baz space 3 space string haha. So if you see something like bar parentheses bar 3, it doesn't mean that bar is called with a bar and 3 as parameters. Yeah, so this doesn't mean it's a function that's taking 2 parameters. It means that the first call to the function bar, this one, where does it say that? It means that we first call the function bar with 3, yeah, right here, as the parameter to get some number. Then we call bar again with that number, the outer one. In C, that would be something like bar bar 3, but with parentheses around it. All right, so that is all good. Baby's first functions. Too bad we don't have like a picture to look at. In the previous section, we got a basic feel for calling function. Now let's try to make our own. Open up your favorite text editor and punch in this function. All right, my favorite text editor is Helix. How am I going to run this? Baby.hs. Right. Okay, so we're gonna make baby.hs. And we'll just call double me x equals x plus x. And I will save this. Functions are defined in a similar way that they are called. The function name is followed by parameters separated by spaces. All right, let me just read that again because I was totally spacing out. You ever do that? Like you're reading something and then you're like, what did I just read? Functions are defined in a similar way that they are called. The function name is followed by parameters separated by spaces. Right, so that makes sense. So we have the space and the parameter. We only take one parameter for this one. But when defining functions, there's an equal sign, and after that we define what the function does. Save this as baby.hs. I guess the hs is the Haskell thing or something. Now navigate to where it's saved and run ghci from there. Okay, so I'm in the same directory, so I can run ghci and do load baby. All right, it compiled main something, one module loaded. Now that our script is loaded, we can play with the function that we defined. All right, so now we can call double me 9, 18. Oh, look, it did a good job. 8.3. And then we should get used to using negative numbers. Force ourselves to use negative numbers. Negative 10. So that's negative 5 plus negative 5 gives you negative 10. Because plus works on integers as well as floating point numbers, anything that can be considered a number really, our function also works on any number. Right, because it's saying that since we're defining it based on plus, that's the only thing we use, then pretty much it should work on anything that plus works on, which is any number. That makes sense. Let's make a function that takes two numbers and multiplies each by 2, then adds them together. Okay, takes two numbers, multiplies each by 2, and then adds them together. All right, so I assume I can just like put this in the same file. Double us, and it takes two variables, two parameters now, and it multiplies each one by 2 and adds them together. Y times 2. There we go. We write this out. Save it and do load baby. Alright, so now I can do double us 4 and 9 like the book suggests, and we get 26. So that is 4 becomes 8, 9 becomes 18, 18 plus 8 is 26. Makes sense, that works. And it works also for floating point numbers. Yep. And our old function is still available. Yes. All right, great. We could have also defined it as double us equals xy is equal to x plus y plus y. That's probably the better way to do it. Junior programmer method. Sounds good. As expected, you can call your own functions from other functions that you made. Oh, wait, did we do that? We didn't do that. So, oh, I see, we're going to do that here. So let's do that. So we'll just get rid of this and we'll call double me x plus double me y. I'm guessing I don't need parentheses around this because this is highest precedence and this is highest precedence, right? Yeah. Now when I load baby again, I mean, we're going to get the same thing, so it's not like the fact that I guess it works is good enough. Oops. There we go. I guess we can just kind of like cheat and make sure that it works by adding 1 to the very end. That way we know we're not like tricking ourselves to believing it works. There we go. We know it's actually working. Cool. This is a very simple example of a common pattern you will see throughout Haskell, making basic functions that are obviously correct and then combining them into more complex functions. You know, like I've been doing the Nix programming for a while, and yeah, for some reason this just feels so much easier. Like, I don't know why though. I guess just because I can just drop things into a file and have those things show up and like not worry about what you have to import and everything like that, and run Nix instantiate and Nix REPL, and so it's kind of funny. Anyway, love Nix. Just a side comment. Making functions that are obviously correct and combining them into more complex functions. Yes, building up. This way, you also avoid repetition. What if some mathematicians figured out that 2 is actually 3 and you had to change your program? You could just redefine double me to be x plus x plus x, and since double us calls double me, it would automatically work in this strange new world where 2 is 3. All right, yeah, sure. Functions in Haskell don't have to be in any particular order, so it doesn't matter if you define double me first and double us and then double us, or if you do it the other way around. Oh, that's so cool. So I can just I can do this where double us is defined first. I'm going to quit out of this just to make sure it doesn't cheat. And it loads. That is really cool. Now we're going to make a function that multiplies a number by 2, but only if that number is smaller or equal to 100, because numbers bigger than 100 are big enough as it is. So when I learn things, I like to kind of just like write it myself, but first I'll take a look at the syntax. I know it's like short-term memory, you can just like look at it and just copy it, but like it helps to just put it away. Double small number x. If x is greater than 100, then it is just x. Otherwise, it's x plus x times 2. So I'm going to put that away. and I'll call double, I even forget what it was called, double x if small. I don't know what they called it. So we have one parameter because it is just x. And we say if x is greater than 100, was there a then? I think there's a then. Then we just return x. And then, but if it's smaller, then we return x times 2. Or double me. Double me x. Let's see if this loads or if I failed somewhere in here. Load baby. All right, so double, does this have tab complete? Double x if small. Oh, can tab, awesome. And I do like 4, it gives me 8. But if I give it 101, it just gives me 101. All right. Oops. Double small number. That is probably a better name. Double small number x. If x is greater than 100, then x, else x times 2. Right. But I used a function we already defined. So that worked. Right here we introduced Haskell's if statement. If you're probably familiar with if statements from other languages. The difference between Haskell's if statement and if statements in imperative languages is that the else part is mandatory in Haskell. In imperative language, you can just skip a couple of steps if the condition isn't satisfied. But in Haskell, every expression and function must return something. We could have also written that if statement in one line. That's what I did. But I find this way more readable. Yeah, I'm just lazy, I think. Another thing about the if statement in Haskell is that it is an expression. An expression is basically a piece of code that returns a value. 5 is an expression because it returns 5. 4 plus 8 is an expression. X plus y is an expression because it returns a sum of x and y. Because the else is mandatory, an if statement will always return something, and that's why it's an expression. If we wanted to add 1 to every number that's produced in our previous function, we could have written its body like this. Oh, isn't that so funny that I did like that for the previous one? That's funny. All right. It wrapped it around the if statement because this is an expression itself. Like all of this is an expression. So you can wrap it in an if statement that turns into a value, and then you just add 1 to it. Had we omitted the parentheses, it would have added only if x wasn't greater than 100. Note the, what do we call this, apostrophe? Tick? I guess tick. Note the tick at the end of the function name. Oh, the apostrophe doesn't have any special meaning in Haskell syntax. It's a valid character to use in a function name. We usually use tick to either denote a strict version of a function, one that isn't lazy. Oh, that's what that means. Or a slightly modified version of a function or a variable. Because tick is a valid character in functions, we can make a function look like this. Conan O'Brien. It's a me, Conan O'Brien. Yeah, so we can have function names that have ticks in them. Don't try to imagine what that means. That doesn't mean anything. Okay. Right? Can I do this? 1, 2, 3, 4. There we go. So yeah, it doesn't care. This is just another character for it. Doesn't this look somehow like obscene, even though I have no idea what it is? I'm gonna get rid of it. I don't want anyone to get me in trouble. All right, so where are we now? There are two noteworthy things here. The first is that in the function name, we didn't capitalize Conan's name. That's because functions can't begin with uppercase letters. Oh, is that true? Not in scope data constructor. There's something to do with data constructors. I don't know what that is, so we'll find out. The second thing is that this function doesn't take any parameters. Right. Oh, I didn't even think of it that way. But yeah, there's a function that takes no parameters. When a function doesn't take any parameters, we usually say it's a definition or a name because we can't change what names and functions mean once we've defined them. Conan O'Brien and the string it's a me, Conan O'Brien, can be used interchangeably. An intro into lists. Okay, this is a oh, so what we had a small kid here, baby, right? And I guess that's like the thing here. We're doubling small stuff. So this guy would get doubled if we threw him into the doubling function, but a big person wouldn't. It's kind of like what you'd want to define in a video game, like if someone is if you want to help like lower level people level up, then you want to like maybe their first 10 levels it's small, so like XP is doubled, but otherwise um it's normal. Yeah. uh, Much like a shopping lists in real world, lists in Haskell are very useful. Milk, bread, eggs, a dog. All right, someone's trying to sneak a dog in. It's the most used data structure, and it can be used in a multitude of different ways to model and solve a whole bunch of problems. Lists are so awesome. In this section, we'll look at the basics of lists, strings, which are lists, and list comprehensions. In Haskell, lists are homogeneous data structures. They store several elements of the same type. That means we can have a list of integers or a list of characters, but we can't have a list that has a few integers and then a few characters. So here's a list. All right. So lost numbers is equal to, I don't understand the reference here. 16, 23, 42. Lost numbers. This is coming out, right? Yeah. Okay, so we see those numbers, but I assume if I try to do something like a list, well, here's our normal list. And if I try to add a string in here now, it doesn't like it. All right, so it has to all be the same type. So does that mean like a floating point number can go in here? Yeah, that's fine, because what it did, it looked like, is it made it all the same by turning all the integers into floating point numbers. That's pretty cool. As you can see, lists are denoted by square brackets, and the values in the list are separated by commas. If we try to list like this, oh, that's what I kind of did, Haskell would complain that the characters, which are, by the way, denoted as a character between single quotes, are not numbers. I see. So this is a character, and this is a string. Okay. Speaking of characters, strings are just lists of characters. Hello is just syntactic sugar for this list of single characters. Oh, cool. So does that mean it'll print out like foo if I just do this as a string? Yeah, that's cool. All right. A common task is putting two strings together. This is done by the plus plus operator. All right, so we have foo plus plus bar. Look at this. We're learning. Isn't that cool? I don't know. It's kind of cool. It's like consistency. It's like you learn the base rules and you can apply it. Like that's what makes it kind of neat, right? Otherwise, yeah, foo plus plus bar would work. And we can make a list like 1, 2, where was that one? Plus plus a list with just one thing in it. Yep. And it added the 1.0 at the very end. Looks good to me. Watch out when repeatedly using the plus plus operator on long strings. When you put together two lists, even if you append a singleton list to a list. For instance, 423 plus plus 4. Internally, Haskell has to walk through the whole list on the left side of plus plus. It's not a problem when dealing with lists that aren't too big, but putting something at the end of a list that's 50 million entries long is going to take a while. However, putting something at the beginning of a list using the colon operator, also called the cons operator, is instantaneous. So joining a single element to a list, like I guess like this, I can put a 0 in the front, so I do 0 colon, and that adds a 0 to the front of the list. And I can add a letter to like A to a list that has B and C already in it. Okay, that's good. And that sort of makes sense, right? If this is implemented internally as some sort of like linked list and you want to add it anywhere other than the front, it's going to take the number of characters or number of items in the list that you have to traverse to get to the position you want to insert it into to do it. So the very first one is constant time because it's always 1. It never changes. All right. Notice how colon takes a number and a list of numbers, or a character and a list of characters, whereas plus plus takes 2 lists. Even if you're adding an element to the end of a list with plus plus, you have to surround it with square brackets so it becomes a list, right? So if I wanted to do the same thing here, I need to add this into brackets, and then I can use the plus plus operator, and it does A, B, C. Because this thing only takes lists to concatenate them. Hi, I love your content. Hi, Mark Van der Meer. I don't know how to say your name. I'm so sorry. Yeah, feel free to chat more, or if you have any questions. All right, where are we? The bracket 1, 2, 3 is actually just syntactic sugar for 1, 2, 3. Oh, this is really cool. So you can like put these together, right? Because this is basically saying 1 being added to the empty list, right? So now it's going to give us 1 inside of a list. And now if you imagine this as like an expression, which it is, now I can add another 1 to this, right? So this is going to be the single list 1, right? It's going to be that thing that you see right above. And we're adding 1 to it, right? So it'll be 1 comma 1. And I could get rid of the parentheses, and it looks like this. So it's saying that that's how lists really are structured, I guess, or this is how they actually are syntactically displayed. So that's really cool. Yeah, note that all of these things are different things. Yes, because the first one, this is an empty string, and this is an empty list. This is an empty list that contains an empty list, and this is this is a list that contains an empty list, so it's not an empty list, right? And then this one here is a list that contains 3 empty lists. Yeah. It's easy to get a little confused, but yeah. If you want to get an element out of a list, use bang bang. The indices start at 0. Oh, I see. So you pass it the position. So if I have like this, I can do bang bang, bang bang, and I do 0. Oops. Probably it doesn't know how to do this. There we go. Yeah, I'm not going to try to figure out the precedence there. So we pull out the first element of 1, 2, 3, and this is the second element, and this is the third element. We'll probably get an error when we do this. Yeah. Index too large, error. You'll get an error, right? So that's what we just did. We tried to go beyond that. Lists can also contain lists, right? This is a good thing to kind of like, oh, right, they do it for us. So I guess I just like typing it out. So here's a list, and it contains a list. And then it also contains another list. And I don't know, do we need another one? Let's do it one more. 4, 3, 2, 1. Yeah. So there we go. B has all of that. And B is a function, right? It's a function that takes no parameters. How funny is that? So that's what B is. And now B, bang, bang. 0 should be 1, 2, 3, 4. And then 1 should be 3, 3, 3. Now, what's interesting is, what if I should be able to turn this into a list too, right? Like here, no, I can't, because it has to all be the same thing. Yeah, this will be an error if I do this, right? No? Why? I don't understand the error, but my feeling is that every element has to be the same, and these are not lists of lists. So these have to all be numbers. Yeah. All right. Well, there we go. That was the whole thing about it being homogeneous that we read about earlier. Wow, we're only halfway through. Oh, I'm going to get tired soon. The list within a list can be of different lengths, but they can't be of different types. Yeah, that's just what we said. So this here could be much longer. And then we can do, we can get that last one by calling 2. There we go. Just like you can't have a list that has some characters and some numbers, you can't have a list that has some list of characters and some list of numbers. Okay, great. So they all have to be numbers. If I put in a list here that is just like of characters, this will fail. Right. Lists can be compared if the stuff they contain can be compared when using less than equal, greater than, or greater than equal to compare lists. They are compared in lexicographical order. First, the heads are compared. If they are equal, then the second elements are compared, etc. So that makes a lot of sense, especially since you kind of like say like strings are, like strings are just lists of letters. So it's just going to compare this as if it was a list. And so now I should be able to say A, B, C is less than. That makes sense. I don't think I'll have to type all of these in. I think I get the general idea. I'm guessing like one thing is like if you have a list, right? This list is going to be the same as this, right? But what if I add like one more? Then I'm guessing that this list is smaller now, right? Yeah. And what can we do? Not takes in like one parameter. Okay, just checking out if I understood. What else can you do with list? There are some basic functions that operate on list. Head. brings the first element of a list. So we give it like 1, 2, 3, and it returns 1. Head of foo returns F. Oh, I thought I typed it in wrong. Head of foo returns F. Okay, we get it. Tail takes a list and returns its tail. In other words, it chops off a list's head. Well, that's pretty gruesome, right? So we do tail 1, 2, 3. This should return the list 2, 3. And tail foo should be oo. And just remembering how we write this other stuff. Isn't that right? Wait, did I forget how we do this? 3. Oh, it's just an operator precedence thing. Right. Tail is going to bind to the 1, and then it gets confused like, what's this colon thing? So we need to do that, and then we get 2, 3. There we go. It's good to check stuff out as much as you can. Last takes a list and returns its last element. So that's a dangerous one because it's very pricey, right? It has to traverse the whole list. You can see I'm getting hungry. Last food is D. Init takes a list and returns everything except its last element. So it's like I should get foo when I pass in food. Yeah. And the same thing with 1, 2, 3. We will get 1, 2. We think of a list as a monster. Here's what's what. If we think of a list as a monster, here's what's what. This is a very scary monster, isn't it? This is called a caterpillar, right? With a big... So its head is the very front. Its tail is everything if you chop off the head. Last is the very end. And init is basically everything if you chop off the last. So, but what happens if we try to get the head of an empty list? Good question. You get an error, or a tail of an empty list, or an init of an empty list, or a last of an empty list. They're all going to give us errors. Oh my, it all blows up in our face. If there's no monster, it doesn't have a head. When using head, tail, last, and init, be careful not to use them on empty lists. This error cannot be caught at compile time, so it's always good practice to take precautions against accidentally telling Haskell to give you some elements from an empty string. Oh, that is scary, right? Like, you never know if you're doing something that's bad like that. Length takes a list and returns its length, obviously. I'm guessing that actually has to traverse the list. Length 4, 4, 4, 4 gives us 4, and then 5 gives us 5. And I assume this one we can give it an empty list. Yeah, 0. Null checks if a list is empty. If it is, it returns true, otherwise returns false. Use the function instead of XS equals empty list if you have a list called XS. All right, so null on empty list is going to return true, and null on something that's not an empty list is going to return false. I assume this is an empty list. Yep, makes sense. We will continue on. Reverse reverses a list. So reverse, and we'll call it doof returns food. And I think this one should be able to work on an empty list, right? Take takes a number and a list. It extracts that many elements from the beginning of the list. Watch. So it's a little bit like a knit, right? It chops the tail, but now you're telling it how big the tail is. So if I give it like 1, then it'll just be F. And if I give it 2, it'll be FO. Right? And then if I do length, take length food, then it'll give me the whole thing. And then if I give it +1, what do you think will happen? It doesn't care. All right. See how if we try to take more elements than there are in the list, it just returns the list. Okay. Cool. Drop works in a similar way, only it drops the number of elements from the beginning of a list. I'm not going to remember all of these, so I won't bother trying to do it. Drop is like take. Maximum takes a list of stuff that can be put in some kind of order and returns the biggest element. Oh, that's pretty cool. So anything that has like greater than equal sign, probably we can use maximum with. So we can do like maximum zoo, and that'll be a z, and maximum like far 3 1 1000, that'll be 1000. And minimum does what you expect, I think. Sum takes a list of number and returns the sum. So here we go, sum. It returns the right number. Product takes a list of number and returns their product. That's cool. And I'm guessing like sum won't work on a string because it can't work on a list of characters. But it probably works fine with floating point numbers. lm takes a thing and a list of things and tell us if that thing is an element of the list. It's usually called as an infix function because it's easier to read that way. For, is it an element of this list? Oh, I see. Okay, so I can do like z, is it an element of this list? Right, but G is not. All right, and that is the same as saying, is G an element of this? And it's false, but Z would be. Right. You know, I still like the prefix notation. Maybe it's just I'm used to it. Those were a few basic functions that operate on list. We'll take a look at more list functions later. Data.list. Okay, that can be later. Texas ranges. Let's do a little bit more. How long have we been on for? This thing tells me somewhere. I just don't know where to look. But anyway, we'll continue here. Texas ranges, and here's kind of like a sheriff looking guy because he has a star here and the Texas mustache and hat. What if we want a list of all numbers between 1 and 20? Sure, we could just type them all out, but obviously that's not a solution for gentlemen who demand excellence from their programming languages. Instead, we'll use ranges. Ranges are a way of making lists that are arithmetic sequences of elements that can be enumerated. Numbers can be enumerated, 1, 2, 3, 4, etc. Characters can also be enumerated. The alphabet is an enumeration of characters from A to Z. Names can't be enumerated. What comes after John? I don't know. True. To make a list containing all the natural numbers from 1 to 20, you just write bracket 1 ... 20 bracket. So let's try that out. 1, 20, And we got all our numbers. That is equivalent to writing what we see here. And there's no difference between writing one or the other except that writing out long enumeration sequences manually is stupid. All right, this is so judgy, right? Like, I've probably done this. Now I feel judged. All right, so we can put in characters. So we can do A through C. And in this case, it's actually kind of stupid, right? Because I could have just typed this with a lot less. So manually typing is not always stupid. Ha. All right. So what? So it looks like you can do ranges between capital letters, right? That's separate. But what if I make it like lowercase to capital? What happens? No, it doesn't like it. And the other way the same, right? Oh! What just happened here? That looks like a regular expression, doesn't it? Isn't that funny? Okay, one day we'll have to figure out what that means, huh? Huh. Yeah, don't know. We'll have to figure that out. Ranges are cool because you can also specify a step. What if we want all even numbers between 1 and 20, or every third number? So we do 2, 4, all the way through 20. Oh, that's cool. So we do 2, comma 4, and then we say all the way through 20. So it knows that this first one is a step. It's going to use the obvious step, just simple like difference between the two, and continue that. And if I used a bigger step, then it'll give me all the multiples. Oh, it'll just keep adding the by 3. Okay. It's simply a matter of separating the first two elements with a comma, then specifying what the upper limit is. I wonder, like, so do you think I can do like, can I do like 2, 4, 6? No, it has to be two numbers followed by 2 periods. Dot dot. While pretty smart, ranges with steps aren't as smart as some people expect them to be. You can't do, oh, this is just what I did, and expect to get all the powers of 2. Firstly, because you can only specify one step, and secondly, because some sequences that aren't arithmetic are ambiguous if given only by a few of their first terms. Yeah, it's like an IQ test there, right? To make a list with all the numbers from 20 to 1, you can't just do 20 to 1. Oh, that's what I was doing before. You have to do 2019 1. Oh, I see. So we go 20, comma 19, dot, dot, 1, and that'll make it down. So if we try to do that for letters, so that means I cannot do Z to dot dot A. This doesn't work. Right. But I can do Z. I can do Y dot dot A. There we go. All right, so we're figuring some stuff out. Now, can I do this? No. No, it doesn't know how to do that. Between Z and A, there are symbols in ASCII. That's why. Oh, you think so? It looks like a regular expression, though. Yeah, it's so funny. Thank you. Watch out when using floating point numbers and ranges because they are not completely precise. By definition, their use in ranges can yield to some pretty funky results. Oh, wow. All right, so ranges with floating point numbers are funky. Thank you for checking for me. All right, so we're gonna see. There we go. Yeah, that's not quite how most people would have done it. but it kind of makes sense. Um, my advice is not to use them in list ranges. Makes sense. You can also use ranges to make infinite lists by just not specifying an upper limit. Later, we'll go into more detail on infinite lists. Oh, you're learning Haskell also? So cool. Um, for now, let's examine how you would get the first 24 numbers of 13. First 24 multiples of 13. Okay, I just skipped a word. Sure, you could do 1326 dot dot 24 times 13, but there's a better way. Aha. So we make an infinite list. So what happens if I type in an infinite list? Is it just going to fail? Oh crap. All right, so that's not good. So we have an infinite list and we can do take from it. Like take 1 should just return 13, which is a little bit like head would just return the number. Oh, right. I don't need this. That just returns the number 13 instead of the list with 13 because take returns, it's still a list. Head takes out the element. And then we said let's take a few of these elements like the first 10, and now we have the first 10 multiples of 13. All right, cool. Because Haskell is lazy, it won't try to evaluate the infinite list immediately because it would never finish. Right. So when I typed it, I'm basically asking it to evaluate it immediately, and then it just goes on forever. It'll wait to see what you want to get out of that infinite list. And here it sees you just want the first 24 elements, and it gladly obliges. Okay, cool. A handful of functions that produce infinite lists. Cycle takes a list and cycles it into an infinite list. If you try to display the results, it will go on forever. Okay, so cycle is going to just make a, we'll just do take 10 for all of these. Cycle can make a list just loop forever. So it's 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. We don't like that, right? We should make it 9. There we go. That was cycle, and it works with it works with strings also. So if you did LOL, it wouldn't have a space in it, so it would just be lol 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 lol. But if you do this, then you'll have a space between them. So that was cycle, and then there's repeat. Repeat just does the same thing forever. So we do repeat. I guess I can give it a single element like A, and then I'll just get 9 A's, or I can give it like a 1. Yeah. So here, unlike cycle, it doesn't take a list. This just takes a single element. Although it's simpler to just use the replicate function if you want some number of the same element in a list. Replicate 3, 10 returns 10, 10, 10. Okay, so this is more like a finite number of times that you want to repeat something, whereas repeats forever. We're actually getting pretty close to the end here, no? You think we can make it? I think I'm going to stop at tuples. That's my guess. All right, I'm a list comprehension. All right, what's the connection between Kermit the Frog and a list comprehension? He's green. He's a frog. Okay, this is like a real reach, but I'm guessing like, Kermit the Frog, he sings Rainbow Connection. How does it go? Why are there so many songs about rainbows? What's on the other side? And Rainbow Connection is like list comprehension. It sounds very similar. Do you think? Am I totally reaching? All right. If you've ever taken a course in mathematics, you've probably run into set comprehensions. They're normally used for building more specific sets out of general sets. A basic comprehension for a set that contains the first 10 even natural numbers is this thing. We're basically saying get us all the natural numbers that are less than or equal to 10, and then multiply each one by 2. The part before the pipe is called the output function. X is the variable. N is the input set, that is natural numbers. X is less than or equal to 10 is the predicate. That means that the set contains the doubles of all natural numbers that satisfy the predicate. All right, cool. If we wanted to write that in Haskell, we could do something like take 10 and then give it the range of 2 comma 4 dot dot. But what if we don't want doubles of the first 10 natural numbers, but we want some kind of more complex function applied on them? We could use a list comprehension for that. List comprehensions, List comprehensions are very similar to set comprehensions. We'll stick to getting the first 10 even numbers for now. The list comprehension we can use is x times 2. That looks like this 2 times x. The bar, and then x and is less than, well, takes, I guess, 1 through 10. X is drawn from, I guess I should say that, X is drawn from the list 1 through 10, or the range 1 through 10. And for every element in 1 through 10, which we have bound to X, we get that element only doubled. Here's the comprehension in action. Let's try to write that if I try to remember. What is it like? X times 2 bar, and then we do X is drawn from the list 1 through 10, right? Something like this. Yeah, that worked. Is that how they wrote it? Yep. All right, that makes sense. As you can see, we get the desired results. Now let's add a condition or a predicate to that comprehension. Predicates go after the binding parts and are separated from them by a comma. Let's say we want only elements which doubled are greater than or equal to 12. I see. So we have a comma, and then we check it's whatever our predicate is. So we want something where when it's doubled, it's greater than or equal to 12. All right, so I'm going to try to not look there. And then I remember it's a comma, and then we just give it the expression, the predicate. X times 2, when it's doubled, is greater than or equal to 12. I think that was it. Yeah, there we go. Cool, it works. How about if we wanted all numbers from 50 to 100 whose remainder when divided with the number 7 is 3? Okay, so there's a mod. So let me not look here. And all numbers from 50 to 100. So maybe we should just turn this to x. And then we do 50 to 100, whose number when divided with 7. So this is like number divided by 7 is 3. This is going to give me floating point math though, right? Yeah, I saw they had mod, so I'm going to use mod. And that's equal to 0 because it means that, oh, whose remainder when divided by the number 7 is 3, right? So we just do this. All right, so is this right? Do we need parentheses around it? I don't think so. All right, is that right? Yeah, all right. I read this wrong, so I was confused. Whose remainder when divided? I just read who when divided with a number the number 7 is 3, which is a little bit different. Yeah, that's just ADHD. All right, let's continue. Success. Note that weeding out lists by predicates is also called filtering. We took a list of numbers and we filtered them by the predicate. Now, for example, let's say we want a comprehension that replaces each odd number greater than 10 with bang. Wait, I'm confused. Each number greater than 10 with bang and each. Oh, okay. So I was thinking that we're going to end up with a list where we have um, some numbers and strings, and we can't have that in Haskell. It has to all be the same thing. So any odd number greater than 10 with bang and each odd number that's less than 10 with boom. If a number isn't odd, we throw it out of our list. Okay, that makes sense because at least now we're going to create a list that is um, yeah. La, 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 la. Oh wait, why are they doing it this way? Because it wants to be passing in the list. But let me just make sure I know how this works. No? So what is the value itself? It seems like what I want to do is actually kind of like define what the the thing itself is. So here I can give it like a list of numbers. So odd. So we'll do 1 through 30, right? And we'll say something like x draws from 1 through 30. And then we'll just this is the easy version. We just have 1 through 30. And now we want to do if x is greater than 10. Well, I don't remember the rules. Was it like, then it's bang? I'll just make it like capital B because it's big. Else, it's a lowercase b. So it should look like all lowercase b's and then all capital B's. Oops. What did it say? Error. No parse error on else. If, then, b, else, lowercase b. There we go. So it's a bunch of lowercase and then it becomes all capital, right? And now we want to give it predicates that are odd. Did it say we filter anything that is odd, right? So that is like x divided by mod 2 is equal to 0. This is all the even numbers. So we say isn't equal to 0. And now we only have the odd numbers, right? Here, let me just type in x here once just to make sure we only have odd numbers. Yep, we only have the odd numbers now. So what did they want here now? Comprehension that replaces each odd number greater than 10 with bang and each odd number that's less than 10 with boom. So greater than 10 with bang. Otherwise, it's boom. And what is the thing we're giving it? 7 to 3. So we'll give it 7 to 13, sorry. And the result is boom, boom, bang, bang. Boom, boom, bang, bang. Perfect. That's what it should be. All right, now we want to write that as a function. So I'll just take this whole thing and put it in here. And we call it boom bang. That's what they call it. Boom bang. X's is equal to, and here we're just going to change the X's. Our hard-coded input from our thing to this. And I think this should actually work. So we will now load our baby and do boom bang 7 to 13, and we get the same result. Isn't that great? Feels good, right? Do we get some dopamine from that? Oh, I see. So they wrote a function odd, or there's a function called odd in Haskell by default. So you can just say odd x. And that works too. That's even better. All right. The last part of the comprehension is the predicate. The function odd returns true. Yeah, we figured that out. The element is included in the list only if all predicates evaluate to true. All right, perfect. So, like, I like making hard-coded stuff first just to explore. That was a lot of stuff. And then you see once you turn it into bang and boom, it's really hard to debug if your odd is working or not. So it's a little bit easier to print out the numbers first. All right. We can include several predicates. If we wanted all numbers from 10 to 20 that are not 13, 15, or 19, we do. Oh, you can just like string along predicates. All right, let's just do that. So this one was, oh. So this is taking in from what range? 20 to 10 to 20. And then predicates said x is not 13, x is not 15, and x is not 19, right? Okay, that worked. I'm pretty sure. Length 8 and length 10 to 20 is 10. So we took away 2. Is that right? 10, 11, 12. We got rid of 13. We got rid of 15. And we got rid of 19. So we took away 3. Right? So length 10 to 20. Oh, that's because I'm just confusing my math. This is actually 11 items because we're including 20. 10 to 19 would be 10. Yeah, duh. All right. We continue. Not only can we have multiple predicates in list comprehensions, an element must satisfy all predicates to be included in the resulting list. We can also draw from several lists. Oh, that's cool. When drawing from several lists, comprehensions produce all combinations of the given list and then join them by the output function we supply. A list produced by a comprehension that draws from two lists of length 4 will have a length of 16, provided we don't filter them. If we have two lists, 2, 5, 10, and 8, 10, 11, and we want to get the products of all possible combinations between those two lists, here's what we do. Oh, I see. It's going to combine all the different possibilities. So x times y is the product, and we're taking in two lists. X is drawn from they have 2, 5, and 10, and then they put a comma. Yeah. Y is drawn from 8, 10, and 11. All right. As expected, the length of the new list is 9. Right, because it has all 3 times 3 is all the ways that those things can be combined. What if we wanted all possible products that are more than 50? Right, then we just add the predicate at the end, right? We just say x times y is greater than 50. So yeah, that worked. How about a list compression that combines a list of adjectives and a list of nouns? Oh, that's pretty cool. Let's write that. Um, Adjective noun. I'm putting it here just because I want to keep it. So we'll make a bunch of nouns. Let's use the nouns they have. Hobo, frog, pope. All right. And adjectives. Lazy, grouchy, scheming. So if I wanted to write this function that takes in, so it takes in a noun and an adjective, let's say. No, it's taking in a list, and we're going to return all of them. So we have N's and we have A's, right? So here we go. Oh, we don't have to do it this way. We can just like do it like this. So the input is noun takes in from nouns, and adjective takes in from adjectives. And then what we do is we try to combine them. So in the front, we do adjective plus noun, right? Oh, yeah, they have a space in here. All right. Is this going to work? Adjective, noun. Lazy hobo, grouchy hobo, scheming hobo, lazy frog, grouchy frog, scheming frog, lazy pope, grouchy pope, scheming pope. That's cool. So you see the 3 times 3, and now we have like 9 combinations. That's really cool. I had to write something like this in my Nix code, I remember, and it was a lot harder. I had to do like a map and a fold. But here you just like you make a comprehension that draws from 2 different sources and you're set. Really cool. Yeah. I wish I knew how long this is lasting already. I feel bad if it's super long. But I'm still having fun, and we're almost done to tuples. All right. I know, let's write our own version of length. We'll call it length prime. Let's try to understand what's going on here. Length prime x's is equal to sum where we have, that's so smart. That's so smart. All right, do you guys see how this works? Yeah, so if we just do like, without the sum, right? If we just give it like the list comprehension, let's do the list comprehension 1. We always are going to print out a 1. It's always going to become a 1 no matter what the input is, right? So we can even say like x takes in from x's. I guess this should work. So we give it like 1, 2, 3. And you can see like the x here doesn't matter because we're not using it here. Like if we used it here, it'd be 1, 2, 3. But we're saying we don't even care about x. We're just always going to be 1. So now for each one of those x's, it's just going to put a 1 in the front. And then we call sum on this whole thing, and we get 3. So if this thing is a 4, then it's a 4, or, whatever. 5 elements, then it's going to be 5, right? So that's pretty cool. That's what it's doing here. Underscore means that we don't care what we'll draw from the list anyway. Yeah, so a lot of programming languages have this underscore thing. I know Elixir does, Rust does this. So instead of writing a variable name that we'll never use, we just write underscore. This function replaces every element of a list with the number 1 and then sums that up. This means that the resulting sum will be the length of our list. Just a friendly reminder, because strings are lists, we can use list comprehensions to process and produce the strings. Here's a function that takes the string and removes everything except uppercase letters from it. You think we can write that without looking? Remove upper, and it takes like letters. What should we call letters? L's? Okay, so we know we're gonna take in L's, so we do L is taking in from L's. Let's just call it X's. I think Haskell likes X's. So if we do this, oh sorry. Okay, if we just do this, then it won't remove anything, right? So we'll reload this. Remove upper foo. Okay, we get foo. We want to make sure we remove upper cases. So eventually we should get food. That is a literal reminder for me. And now I think we can make a predicate, right? So we want to say, we want to know if it's, do you think it uses ASCII values? Oh no, maybe we should check if it's an element of, right? So we make the range of all capital letters, and we say X is not an element of this. So how do we say not? We do like not? Something like this. So this thing here, X is an element of A through Z, and we say not element. I think element was the thing, wasn't it? Okay, remove upper. Oh, here we have it here. Food! All right. How did they do it? Oh, they do the same thing. Wait. Remove non-uppercase. Hold on, did I do it? I did the opposite thing. Everything except uppercase letters. I read it wrong. I swear that sometimes, if only I could read better, life would be so much easier. Now we just have foo instead of food. That's terrible. Alright, so we can also test like other things. And it only keeps uppercase letters. Alright, that's pretty cool, right? But this should be called keep upper, not remove upper. But my remove upper did work, right? So there you go. We test it out. Yep. The predicate here does all the work. It says that the character will be included in the new list only if it's an element of the list A through Z. Nested list comprehensions are also possible. Ooh. If you're operating on lists that contain lists. A list containing several lists of numbers. Okay, it's a list that contains a list of numbers. Let's remove all odd numbers without flattening the list. Wow. That's really cool, but it's a little bit of a mind thing, right? So we'll do like we'll have list numbers. And that is just going to be equal to this thing. I'm just going to copy it because it's a lot easier. Okay, so we have this. And now we want to go into each one. Well, let's just get the lists. So here is our list comprehension. Do stuff. Do stuff. No. I'm not going to write it this way. I'm just going to store it this way. I'm going to load the baby, and then I'm going to type list of list numbers. We have those. Now I'm going to use that in a comprehension. So we'll say this is a list of lists. So this is x's, just to use their terminology. So x's, since that thing is x's, xx's, we'll just do x's this. And this is going to print out the same thing, right? But now that we have in here, we'll make a big space here just to make sure, like, we don't forget. We start our new comprehension in here. So this is getting a lists of lists, right? And now we want to basically get, we want to say that we're pulling in x's. X is being pulled from x's, right? And here I can just print out the x. Is that right? I think so. Now I'm getting the x, and now I can just check if the x, what is it that we're trying to do? A list contains, let's remove all the odd numbers, right? So we just do this and we say not odd x. There we go. Is that how they did it? Even x. So there's an even function. There we go. Yeah, so pretty much what I wrote. Hope that was clear to people. Oh, what'd you say here? That's a cool person from Blue Sky. Oh, it's me. I would love to learn Haskell one day too. Yeah, Haskell. It's a fun language to learn. I haven't gone very far with it, but I'm enjoying it right now. It is kind of like, it seems so powerful, like typing so little, but then your brain has to work harder for the little that you're typing, it feels like, you know? All right, so I think we'll stop here before going into tuples because it's kind of like a long thing already, and then we can do tuples. It won't take that long. We'll be done, and then we'll be able to do types and type classes, right? Yeah, I'm so tempted to do tuples right now, but I don't think I can, like, I think I should break. I should eat something, and we will continue later. Thank you so much for hanging out with me, those of you on stream and those of you watching. If you enjoy this video, please do like and subscribe. This will be a series, and we have other series on Nix, on Atari 6502. And I just did this COBOL one that was insane. It really blew my mind, like trying to learn COBOL on a mainframe. So that's an ongoing thing too, but yeah, that's a whole thing. So thank you so much. I'll stop the video here. I'll stay on the stream for just a little bit longer. Thank you. Thanks for hanging out with me, y'all. Uh, did you make a bit of it, Dot or Dot Levine, or what did you say? I've tried before. One of my besties was a Haskell maven, and he switched to Clojure, so I followed suit. Clojure is a lot like Lisp, right? I don't know what the difference between Clojure and Lisp is, but I used to use a lot of Scheme. I even used it at work also. So that was pretty cool, but I think Clojure is like object-oriented Lisp if I recall correctly. And I've never used that aspect, but yeah, Clojure seems pretty cool. Although, like, if I were to learn a functional programming language that I want to use for work that's more extreme, I think I would probably do OCaml just because it seems like it's very geared towards being pragmatic and useful, but still has a real strong leaning on functional programming. I don't know. One day I'll eventually learn some OCaml and I'll have a better judgment. You know, it was funny. I talked to a friend of mine, right? And it's like an old friend from high school, and I'm like, hey, I'm learning Haskell, and he's into like computer science. He graduated with a computer science degree and everything. And he's like, Haskell, isn't that academic language? Why are you learning that? And he starts like berating me, like, oh, you're just so silly learning like Haskell. You can't do anything with it. And then literally like, I'm not working right now, but I'm starting to like look for something. So, I call a friend and he's like, "Yeah, you should meet these guys. Like, they might have a position, right?" So I called them up and I said, "What language do you use?" And they're like, "Haskell." This is like the day after I talked to my friend, right? And I'm like, "You use Haskell?" Like, I was just people were just making fun of Haskell, and he's like, it was the CTO, and he was like, "Oh yeah, the companies like us that are using it, we're not very loud. We don't talk very much, but we exist and we're a very tight group." And I'm like, oh crap, what are the chances, of all the people I talk to next, they're actually using Haskell? So that was pretty cool. So I think any language you can kind of like get a job in. They were doing some kind of like data analysis and they were just saying like, yeah, it's really useful to have like a language that you can feel like is actually correct. You can check for correctness a lot better. Yeah. So that's my little story. Are you using Elixir for work? Yeah, I use Elixir for my projects. Some of and like I do a lot of freelancing, so like client projects, I use Elixir. I really love Elixir. I went through a phase where I didn't love it as much just because like it's all dynamic kind of typing. But like you can get pretty strict typing if you use dialyzer and you use like a lot of guards. So it's not as bad as like JavaScript or something like that. But yeah, I really do like Elixir mostly because it's on Beam and it has like crazy concurrency system with OTP. I just love it. It's so good. I program mostly on the server side, and I really need to try out the live view stuff because it's basically you use Elixir on the back end to render all the front end web pages. I don't do much web stuff, but you know, that's because I hate JavaScript and CSS and all that stuff, right? So if I can actually use like Elixir to do all that, then maybe I would like it a lot more. Uh, Switching from NeoVim to Emacs. Yeah, I used to use Emacs a long time ago. Now I'm using Helix. I kind of like Helix. It feels like it feels like NeoVim with just less. So I have to kind of get better at it though. I knew all the Emacs bindings, but all the control and the pinky keys, like it's so tiring after a while with Emacs. Closure is pretty strictly functional. OCaml strengthens the type system. Yeah, that's what I like about Haskell too, is the type system is really cool. So I want to learn more about that. Haskell seems to be rare in production. Another academic friend of mine uses it in his academic work. Yeah, it seems like a lot of papers are written with Haskell. So that's pretty true. All right, looks like we're at the end of chat then. Thanks so much, everyone. I will be doing more. I think the way I'll be doing this more is like whenever I make a video, I'll just make it a stream at the same time. But I don't have a schedule, so it's just whenever I guess I have time and feel like it, which is most of the time. The problem is more like after a while of talking, it's really hard to continue.